about Garrett Schieber's work. Garrett is a PhD student in mechanical engineering at Georgia Tech, and he's also a graduate research assistant in the Solar Fuels and Technologies laboratory there. And Garrett is also a member of the REVEALS team. So he received his bachelor's in 2015 in mechanical engineering from Iowa State University and his master's in mechanical engineering too from Georgia Tech in 2017. And currently he specializes in water transport within regolith, concentrating solar utilization on the moon, and that's what we're going to hear about today. And just as a note, Garrett was also president of the Iowa State Lunabotics Club, which participated in NASA Lunabotics mining competitions. So you have a long relationship with regolith and resource extractions from regolith.
Yeah, at least in
some.
Okay. Okay, so I guess I'll get ready and begin. Can everyone see that?
Yes.
Okay. So, hi again. My name is Garrett, and thanks. You pronounced my name correctly the first try. That was yeah. My name is Garrett Schieber, my project and what I'll be presenting on today is REVEALS research in ISRU, transport of gases at lunar conditions, and then I'll mention concentrated solar utilization on the moon. And so again, a lot of this is repeat, but PhD student from Georgia Tech, member of the REVEALS team. And my background is in mechanical engineering, focused in the thermal sciences. And like she mentioned, I was pretty heavily involved with Lunabotics as an undergrad. For any of you who don't know that, Lunabotics is a robotic mining competition where the goal is to collect as much lunar regolith simulant so NASA can evaluate ideas for basically collecting that material on the moon. And so when I came into into grad school, excuse me, I joined a solar lab focused in the thermal sciences, and my advisor was like, "Oh, that's a really cool project, but you'll probably never work with regolith again." And I was like, "Okay, I still really like solar, but anyway." So a couple of years later, we get approved for REVEALS, and I was like, "Oh wow, I'm working with regolith again." My advisor was wrong, and it was very interesting how I kind of came back to regolith after a couple of years just focusing primarily on solar. So anyway, I wanted to give a quick background I'm sure all of you, or most of you, kind of know the concept behind In-Situ Resource Utilization, but what is ISRU and what is In-Situ Resource Utilization? So ISRU is requiring the resources needed for a space mission on site. So the reason that you'd consider using or doing ISRU is because launch costs are expensive, up to $10,000 a pound, and maybe even greater to get to the moon. To launch the material into low Earth orbit. And a permanent moon base without ISRU is currently infeasible due to these high costs. And so that's the motivation kind of in general for ISRU. And so today, the first thing I'll talk about is go over a volatile transport model and work that I've done. I'll go through an introduction and motivation to that work. I'll talk about some basic theory, then I'll talk about my experiments. Then I'll go through and how we are working to characterize and understand the pore structure of porous media. I'll talk about how I characterize transport, and then I'll talk about some results. And then as a second part, we'll talk about solar and future work that my lab is looking into. We'll talk about kind of the solar resources on the moon and an ISRU experimental setup that we have. So the introduction and motivation to the volatile work is that lunar regolith contains ice and other trace volatiles. So icy regolith may contain more than 1% weight of water ice, and that water ice is of course incredibly relevant towards ISRU because for things like human consumption for human bases, and then for processing into rocket fuel. And you can process water vapor to rocket fuel through things like electrolysis and other technologies. So water is an incredibly valuable resource. And so there's a couple concepts for extracting the water vapor from permanently shadowed craters in areas where you have high concentrations of water. And so one technology is called thermal extraction, and that's where you beam solar energy into a permanently shadowed crater to extract H2O. And I drew a quick kind of schematic of that, where, for example, you could have a tent where the radiation would be able to shine through that tent and heat up the regolith, collecting the water vapor. And that one is called specifically thermal extraction. And then there's other ones such as drilling and sampling that will also cause heat transfer and H2O transport and escape. So understanding and modeling both heat and mass transport is key for engineering these ISRU systems. And so now let's talk a little bit about like the theory behind this and what we can research about this. So low pressure. So first I'll talk, like I said, low pressure transport theory. So on Earth, we generally operate at the continuum. And what the continuum is of course, like in air, we can treat air as a continuous medium, and we don't have to worry about individual molecules. Where on the other end in space, of course, we have to worry about, we cannot treat space as a continuum, and we have to treat it as individual molecules. And so there's a dimensionless number called the Knudsen number that helps us understand if we can operate at continuum or if we have to operate at free molecular flow conditions, or the Knudsen conditions. And so the Knudsen number is the ratio of the mean free path, or the distance between molecules to the distance to walls. And so what this means is that on Earth, we have very, very low Knudsen numbers. And that's because the distance between molecules is very, very small. While in space, of course, we have free molecular Knudsen conditions because the distance between molecules is so large. And then there's a couple of regimes in the middle where these effects compete. And so let's identify our flow regime of interest. And so first, if I'll get to how I approximate the pore diameter of packed beds of lunar regolith. But if we set that pore diameter, and then we assume that we have a water vapor at 400 Kelvin, kind of what pressure of that water vapor would be necessary to achieve these Knudsen numbers. And you can see that to get to continuum, you'd have to have quite high pressure of water vapor. Where on the other end, to get even into the transition regime and full free molecular flow, you'll only require 300 pascals. And pay attention too that this is a logarithmic scale. That's how these regimes are divided up logarithmically. So now, as to try to evaluate what regime causing this water vapor to evaporate would result, like where we would be in, I said, let's say we have regolith with a little bit of water ice, and we volatilize 10% of that water ice. What would that pressure be within the pore structure? And so, what weight percent of water ice would be would result in these pressures? And I calculated that surprisingly, that if you can volatilize 10% of the water ice with just 3 weight percent of or 0.3 weight percent of H2O, you can actually achieve pretty high pressures if it was all at 400 Kelvin. Now, of course, you're not all going to be at 400 Kelvin, and there might be some other time constants involved. But either way, I think it's actually pretty likely that you'll be in this transition regime, and maybe even in the slip regime if we're actually shooting for this highly saturated lunar regolith. And so basically, I looked at these regimes and found that there wasn't a lot of understanding of how transport works kind of in this transition and slip regimes at lunar-like conditions. And so then my research challenge was to characterize volatile transport through regolith and determine which bulk characteristics of regolith are important for this volatile transport. And so if we looked at the Knudsen number again, basically I have a fluids characterization or characterizing whatever fluid or gas is flowing through the regolith. And then I have to characterize the porous media to effectively capture the Knudsen number. And so I found through literature reviewing that advances actually need to be made in both characterizing the fluid and gas and how that transports at different Knudsen regimes, and also characterizing the porous media. And so then I also chose argon and nitrogen as the first step towards a more complete understanding of gas transport. And argon and nitrogen were chosen, again, as that first step, because there was still some fundamental theory that wasn't defined even for ideal gases. And so moving forward in the future, H2O will of course be studied, but this study, we still had some interesting results with just this argon and nitrogen. And so how my experimental, and so now we'll move on to my experimental setup. So my experimental rig is set up from testing from one torr all the way up to 400 torr of pressure differential. And the way it does this is I have a gas tank which has a specific gas, and I have a flow controller or a set of flow controllers that allows me to very precisely and very precisely dose gases into my system. And these flow controllers go from the very, very low range to simulate very, very low concentrations of water vapor all the way up to very high flow rates with a different flow controller. That flows in, and I have a valve to make sure I'm not flowing when I don't want to be flowing. And then I have a pressure transducer, a differential pressure gauge, a convection gauge, all to monitor pressure and make sure I'm getting accurate measurement. I have a custom sample holder assembly that allows me to control things like porosity in my packed bed and relative density. And then, so the gases flows through in this direction, that packed bed. And then I have a fine mesh, and that fine mesh is specifically tuned to where it's smaller than the particles, so it doesn't let the particles out, but its pore size is larger than that of the actual regolith simulant. And so that way the screens don't add any extra blockage to the flow. And so then on the other end, I have more pressure transducers and another convection gauge. And then I have a vacuum pump to make sure we're actually simulating lunar-like conditions. And so the system is then vacuumed out. So testing was conducted under steady state conditions at ambient temperatures, and the steady state allowed me to isolate transport constants. And ambient temperatures was, again, that first step. So we have that fundamental understanding that we can build upon. And future study will include higher temperature. So this initial work was conducted with JSC-1A. And that was at least the most available simulant to me at the time. And I actually took some microscopic imaging. And so you can see how this pore structure would be, of course, very complex. And I think that's just an interesting image of JSC-1A. And so then I wanted to provide a visualization of the data I would get from this experimental apparatus. And so pressure was the primary thing measured with my experimental apparatus, of course. And so on this, on the y-axis, I have delta P. On the x-axis, this is the thing I controlled. I have the mass flow rate, and the mass flow rate, and this is standard for mass flow controllers, was liters per minute. And so you can see basically on this plot that as you get to higher flow conditions, you see a linear increase, and that's expected because that's as we're getting to the continuum. Where on the other end, it doesn't look as linear, and I actually had to shift to a log scale to see the lowest pressure regime. And so you can see that here. Okay, so now let's get to how I can work and process this data and figure out how to model this transport. So now let's first talk about how I characterize porous media. So porous media are essentially a system, when considering transport, are essentially a system of microchannels with a lot more complexity. So pore size, it would not be uniform in this case, and you can approximate that with an average pore diameter. The path, and also the path is not straight, and so you account for this with a parameter called tortuosity, which I'll explain in coming slides. And to characterize both pore diameter and tortuosity, correlations are used. And the correlations relied on something known as porosity, which is void fraction. And then also particle size was critical and is probably the most critical thing to understand the pore structure that regolith forms. And so just in case, I conducted some imaging analysis on the JSC1A to determine and make sure that the particle diameter was what was recorded in literature. And just to give some justification for why JSC1A works for this application is because it was chosen because the particle size distribution is close to that of lunar regolith. And so this is from a work by Zhang, and it's the geotechnical properties of JSC1A, a lunar soil simulant. And you can see it's bounded by the lunar soil averages, and JSC1A is right in the middle. And so I think that JSC1A worked well for this, this study, but I actually do have now LMS1 and LHS1, and I will definitely use those for future studies because I believe they're also kind of right there in the middle too. So, and just quickly to show the imaging analysis, and this is a fairly standard process, but we have a in-house MATLAB code that we developed where basically we can take microscopic images of our particles and then process the images and determine basically the average particle size and things like how round they are. But I verified that the average particle size of the batch of JSC1A that I was using was approximately that 105 microns as reported in literature. So that was a good just check and make sure that that the JSC1A was still as reported. And so then I conducted an extensive literature review to determine the most appropriate relationship for pore diameter. And so pore diameter, through my literature review, I found an empirically derived relationship that was dependent on the particle diameter and the pore diameter, and it gave me an average pore diameter based on that particle diameter and the porosity. And so I found through my results that this relationship actually worked the best and matched, and my results would match what we would see in microchannel flow when I used this number to process them. So this was the one I chose and found that was best. And then porosity or void fraction can be found by measuring the sample relative density. And so I utilized a laboratory balance to measure mass, and then I have a sample container with known dimensions and a depth caliper tool to measure the volume. And so that way I was able to accurately measure the relative density. And then using the published particle density, you can get basically what fraction of your space within this packed bed is void space or the void or porosity. And so I mentioned that I would talk about tortuosity. And so tortuosity is a lot more difficult to quantify. There's far less correlations, but what is tortuosity? So tortuosity is essentially if you have flow through a packed bed, what the path that flow would follow. And so I've just drawn a sample so we can understand this, where the red is the path that maybe flow would follow, and the blue is the overall length of the packed bed. Tortuosity is simply the ratio of that length that the fluid would follow over the length of the packed bed. And so with that understanding, I chose tortuosity correlation shown here, where you have a tortuosity factor p tau, and I set it to 0.6, and then it's also dependent on porosity. So the reason I chose p tau as 0.6 is because for this correlation, it was bounded on two ends, where one, the lower bound was p tau of 0.49, which was for perfect spheres of uniform size and shape, and 0.7 for a fibrous non-uniform material. And I said that JSC1A and lunar regolith would be somewhere in between those two numbers, just as an estimation. However, I wasn't satisfied with that estimation. At least, I was satisfied with it for the initial study, but moving forward, I'd like to have a little bit better of an understanding and a way to better get relationships for tortuosity. So I'm developing a computational approach to rapidly simulate and determine tortuosity tortuosity. And it's based off of a method called the path tracking method. The path tracking method utilizes an open source, so there's two parts to it. There's actually basically tracking the path. And the other part is making a computational packed bed. And so I used an open source DEM software, Lights, to make a computational packed bed. And we can see it here. And I was actually able to make very large computational packed beds that way. So the path tracking algorithm is interesting. It doesn't directly simulate physics. What it does is it utilizes the geometry of the bed to determine likely exits and the likely path. And then once it kind of has a couple candidates, it uses physics to determine which is most probable based on the likely exits, at least locally. And so this is actually a research in progress, but I do show an example here where the red dots, where the axes are all position, and the red dots are particle centroids, and then the blue is the path through this three-dimensional packed bed. And so with this work, I will hopefully be able to develop relationships that can be used for all different scenarios, including lunar regolith. So now let's go and look at the theory behind gas transport. And so if you remember, the Knudsen number is used to describe the flow regimes, and it's calculated with the mean free path. And so again, the Knudsen number is this, and the mean free path is this, and it's determined primarily by the temperature of the gas, the kinetic diameter of the gas, and the pressure of the gas. And so I've shown here in the bottom basically the two extremes you can have in a microchannel. One is in the continuum, and you get a parabolic flow profile represented by the black dots. And then on the other end of the Knudsen spectrum, you have free molecular flow, where your molecules don't interact with one another and just essentially randomly bounce through and diffuse through the system based on that bouncing through. And so in the transition and slip regime that I identified as a potential, or as a likelihood that we're going to be in that regime, you actually have this advective or continuum transport combining and competing with the Knudsen diffusion associated with free molecular flow. And so the model I chose to capture this and study was the advection diffusion model, which combines both transport modes, allowing for a complete picture and simulating physics. And so let's talk about diffusion at low pressure. So diffusion at the lowest pressure and the highest Knudsen number is where wall molecule collisions dominate. This is known as Knudsen diffusion, expressed here, where it's primarily going to be dependent on the pore diameter, the average pore diameter of the lunar regolith, and then it's corrected for porous media using the tortuosity and the porosity of that porous media. So then that's not the only diffusion mechanism that we have to worry about. When the Knudsen number goes below 10, when the pressure increases slightly, intermolecular collisions begin to play a role. And this is referred to as ordinary diffusion, where then this is mostly dependent on that mean free path of the gas. And this is again corrected for porous media as that porosity over the tortuosity. So then the total diffusivity is expressed as this, where dt is the total diffusivity. And this is a little bit difficult to visualize, so I went ahead and made a plot where the blue line here, this is just non-dimensional diffusivity normalized to the Knudsen diffusivity, where the blue line is that Knudsen diffusivity, and so we'd expect to have purely Knudsen diffusion as we get to higher and higher Knudsen numbers, and we see that on this right-hand the plot. Whereas we get to lower and lower pressure, or higher and higher pressures and lower Knudsen numbers, we have more intermolecular collisions, which slows down diffusion. And so we see that basically as we get to higher and higher, diffusion becomes very, very small. And so if this mode is used exclusively past Knudsen numbers of 1 or 10, or lower than Knudsen numbers of like 1 or even 10, transport will be severely underpredicted. And that's because you're not the model would not be accounting for advection. And so how do we account for advection? We use Darcy's law. And so Darcy's law is used for continuum transport. And I refer to this as advection. And so with Darcy's law, you have the average velocity, and this is a vector, so this is in all three directions. You have the permeability, this flow constant expresses how easily gas transports through the system. So higher permeability means that gas will more easily transport through your system. And then you have the fluid viscosity, and then you have the pressure gradient. So at low pressure, when the Knudsen number gets below, or above 0.01, molecular wall slip begins to occur. And so slip can be corrected with an experimentally determined Klinkenberg slip coefficient. And so that Klinkenberg slip coefficient is this BK here. And the correction looks like this, where you take your viscous flow permeability and you multiply it by 1 plus that Klinkenberg slip coefficient over the average pressure. And this is because slip actually increases transport because your gas isn't sticking as hard to the walls, and so it enhances transport. And so then to combine these two mechanisms, again, I use the advection diffusion model, and that is shown here. However, there's not much I can do with this, so I have to isolate transport constants so I can study this experimentally. And so several assumptions are made to isolate these transport constants, such as constant mass flow, isothermal, and ideal gas assumptions. So substituting, simplifying, and integrating, we get this expression, which basically, now I wanted to call out a couple things. So when I integrate the average pressure, this results in an average pressure here, and this is actually a consequence of integration. This is not an approximation. And so, and then you see that I have the diffusivity and the permeability there. And where on this side, then I have, this term is equivalent to the mass flow rate, or proportional, excuse me, to the mass flow rate. And this term, of course, is the pressure drop. And so this term altogether is the mass flow over pressure drop. And so at highest pressure, diffusivity is minimal, as I showed, especially minimal compared to advection. And so to isolate and determine kind of that Klinkenberg slip coefficient, you set this as equal to 0. You substitute in your model for permeability, and you get this equation, which then you can do nonlinear regression on. And to do nonlinear regression, I use the Nelder-Mead algorithm, and with a least squares criterion to minimize like chi-squared. And so what that effectively means is basically I took my error at each point based on my experimental measurements, and I factored in that error when doing this regression. So at points, if they had higher error, would be considered less or weighted less in the regression, and points with the lowest error would be weighted the most heavily. So now we can get to the results. And so the results here are shown in this plot to the right. And so let's look at the y-axis first. So if, from earlier, we see that we get this term to the right. And so this term to the right actually has, that's the same units as diffusivity. And so I plotted this mass flow over pressure drop against my Knudsen diffusivity, because Knudsen diffusivity should be the term that my experiment, or the value that my experimental data approaches as the Knudsen number goes to infinity. And so we can see that, and then on this axis, I actually have the average Knudsen number. And I did use the average Knudsen number also because it was convenient for several reasons, because we do have the average pressure here. And also I wasn't measuring pressure directly in the middle of the bed, but average pressure was actually convenient for fitting and stuff like that. And so you can see basically this shape where there's a continuous increase on this side, and then it starts to level off and approach that Knudsen diffusivity. And so this shape is actually very similar to what is seen in microchannel flow. And so that was a good result. And then then as I mentioned here, the model fit the data well when the Knudsen number was less than 1. And as I showed earlier, I believe that this will be the relevant regime for H2O extraction. And so I think that this is a promising result and shows that the advection diffusion model will capture the transport. And also this increase on this side was expected, and that was based on continuum flow, and that matches again that that microchannel flow. And then I then replicated this behavior for argon, and then I replicated it 3 times for nitrogen just to confirm. But I just chose one to show here. And so then on the other side, as I mentioned, the data approaches the diffusivity, the Knudsen diffusivity as the Knudsen number increases. However, the model does deviate right around Knudsen number is equal to 1. And I thought about my model and I identified that this is most likely due to the slip model being used. And so basically, as you get towards the free molecular flow regime, it should just be diffusivity contributing towards transport. However, when you distribute this K and the permeability and the viscosity through this equation, as you get to lower and lower pressures, this term is effectively 0 or hardly contributing to transport. But since I used a constant slip model, basically this term remains, and so you get kind of an offset, and we see that here. And so additional research needs to be done on the fundamental level to identify a better slip model that can be used and basically account for this and not have slip in the Knudsen regime. And so this is a potential for future work kind of on that fundamental level. And so then I wanted to look specifically at the slip regime, because I did actually fit for viscous flow permeability in that Klinkenberg slip parameter. And so I've shown characteristic results for argon and nitrogen in the slip regime. And so you can see here that that the permeability is higher for argon than nitrogen, and that's primarily due to the argon having higher porosity. So the packed bed is more open for argon, so you see that higher permeability, where the packed bed is more closed for nitrogen, so it's lower. And and on the y-axis I have permeability, and on the x-axis I have that average pressure. And so then, and we also see that as we get lower and lower pressure, the permeability increases, and that's because slip is increasing our permeability, and that again was to be expected. And then we have argon. We have argon slipping more than nitrogen, and that too was expected because argon has a smaller kinetic diameter than nitrogen, which means that it's more likely to slip. Now that is particularly interesting because H2O or water vapor has a smaller kinetic diameter than both nitrogen and argon, and so that means that argon or that water vapor is expected to slip a lot more than both of these gases. And so in the table below, I'll show data with 95% confidence intervals. And so you can see that I've identified the gases. We have the relative densities of, so this is for 3 packed beds replicated with the 2 different gases, and the porosities are listed here. And then I have the permeabilities listed and that fitted Klinkenberg slip parameter. And so K was seen to increase with an increasing porosity of the bed for both gases. That was expected. And then the K was shown to be about the same for gases, for the 2 gases, basically verifying that this approach worked in determining permeability with the 2 different gases. And this is the viscous flow permeability. So these numbers right there and right there, right there and right there, right there and right there should approximately match. And so that was a really good result. And then I wanted to talk about this Klinkenberg slip parameter. And so as a result of the nonlinear fit, the reason these, the uncertainty on these is so high is because the error of this term actually compounded with the error of this when I applied that nonlinear fit. And so we see a lot of uncertainty in the Klinkenberg slip parameters here. Now we see that the lowest porosity bed had the highest slip, where the higher porosity beds both had a little bit lower slip. However, because of our high uncertainty, we couldn't make any strong conclusions about any trends for these two gases. Now, if I was just studying argon and nitrogen, I think I would potentially do a more complex study of slip. However, I think moving towards water vapor and understanding water vapor slip would be more valuable for the ISRU in the ISRU context. But this shows too that slip is going to be very important when considering transport of water vapor out of regolith. And so, and this kind of leads to the conclusion. So I demonstrated the advection diffusion model effectively captures transport regimes relevant towards ISRU. I presented a regolith pore structure characterization approach, and I verified models and identified where model improvements were necessary. And this should say transport models. And then I conducted water vapor study is needed to determine the impact of slip, as I mentioned in the last slide. And then both advection and diffusion need to be considered for ISRU transport models. And so that concludes my talk about volatile transport. But now I'll go ahead and mention and talk about our solar and future work. And so to kind of introduce you to the lab I joined, so we're the Solar Fuels and Technology Laboratory. And so we focus on using solar thermal energy to drive chemical reactions so that we can do things like store that solar energy in the chemical form and potentially make things like hydrogen using solar thermal as the heat input. And so to do this, to simulate or to have solar thermal energy that we can use, there's a couple approaches. One is you go outside and you use a mirror and concentrate that. Or what we have done is we use lamps, and these lamps are xenon arc lamps. And so we have something called a solar simulator, which just lets us get on-demand simulated solar thermal energy. And so our solar simulator is an array of 7 high-power xenon arc lamps, and that lets us deliver 6 kilowatts thermal through a 40-millimeter aperture. And so this is a flux map of this system where we see that we can get very high power, especially in the center. And like I said, it's 6 kilowatts thermal, so that's quite a bit of energy. Now, that we don't know exactly, like I can't visualize exactly what 6 kilowatt thermal means, but to help visualize this, we've done this demonstration where we melt through a 1/4 inch thick piece of stainless steel. So if we watch this, we can see that the steel melts away. Now this is sped up slightly, but it's still a very quick process using our lamps to melt through this 1/4 inch piece of steel. And so I think this just helps visualize how powerful these lamps are and how we can use this simulated solar thermal energy to do a lot of interesting things. And so the reason I'm talking about solar is because the lunar conditions are ideal for solar resource utilization. Compared to Earth, there's no atmosphere or clouds, of course, which means the extraterrestrial solar irradiation is going to be the number used. And so on Earth, we see about 1,000 watts per meter squared at the surface, where on the moon, we expect to see around 1,365 watts per meter squared. So that's a significant increase comparatively. And then on Earth, we have a very high declination angle, and that declination angle is responsible for the seasons. So we have, of course, summer and winter, because the Earth rotates and tilts, where the moon has a very low tilt angle, and so we wouldn't expect any that to be as big of an impact. However, what we would expect is because the Earth's distance from the sun is not constant, there is an associated change in solar irradiation due to that. And so there would be a slight seasonal variation due to that. And then another advantage is a big challenge here on Earth is the day is so short that it's hard to get up and operate at steady state for long periods of time. However, on the moon, the day is 14 Earth days. And so that's a lot more time to run these at steady state and heat them up. However, that means a lot longer in the evening, or in the night, excuse me. And so for solar energy, what temperature is possible? And so to answer this question, I can consider a simplified heat transfer model where I have radiation going through a cross-section A, and that radiation is the extraterrestrial level at 1365. It goes through some concentrator and is concentrated and shines on a black body receiver. And so a black body receiver absorbs and emits radiation perfectly. And to express this concentration, basically you take the area of the concentrated cross-section over the area, the inlet area. And so to basically assess how we can get, or how hot we can get, we just do a simple heat transfer model where we take the absorbed radiation from this black body and we have our heat input, which is our this I, or this initial irradiation, which is concentrated. And then we have the heat output, which is just sigma T to the fourth. And so substituting that back in, we have this heat input minus this heat output. And then if we wanted to basically generalize this in terms of efficiency, we can divide our heat input by all our terms and get an absorption efficiency, where it's 1 minus sigma T to the fourth over IC. And this way, we can determine that the receiver temperature is dependent on concentration, or on concentration ratio. And so this way, if we have a temperature target, we can assess which concentration ratio is needed from our concentrating systems on the moon. And so to determine basically which concentration ratio would be needed, I plotted absorption efficiency, or this absorption efficiency I introduced last slide. And then we have on the x-axis the receiver temperature in Celsius. And so this helps us understand which concentration ratio is needed to achieve desired temperatures. And so if I think about something like the thermal extraction of volatiles, we potentially don't need a super high temperature. So if we only say needed 500 degrees Celsius, we could definitely get away and efficiently use a concentration ratio of about 100. Where if we're doing something more advanced that requires higher temperature, for example, melting the regolith or sintering, we're going to need higher concentration ratios to get to those temperatures. And so now we have to ask, like, what concentration technologies are capable to achieve this these temperatures. And so another benefit, though, of on the moon is that we can have a little bit lighter infrastructure facilitated by the absence of wind, and there's a lot less gravity on the moon. And so here's 3 different concepts for how you can concentrate solar radiation. The first one is a trough, and you get the lowest concentration with these. And however, it only requires 1 axis tracking of the sun. And then there is the tower design, where essentially you use heliostats or mirrors to shine the solar radiation into a central receiver. And using these, you can actually get to fairly high concentration ratios, from 500 to 5,000 with a component called a secondary concentrator. However, these require 2-axis tracking. Ultimately, though, however, if you want basically large scalable applications, the receiver heliostat system is potentially the best, because you can make the receiver larger. More so than, for an example would be, the third example would be the dish system. The dish system, you can get the highest concentration. However, it's a lot more difficult to make an incredibly large dish system. And so, like I said, you can get to the highest concentration ratios, but you're going to be limited in terms of how large you can get. And also the receiver kind of has to be at the focus of that dish system. And again, these designs both require 2-axis tracking. And so then some experimental work that we have in progress is we're modifying an existing system called the upward flow reactor to simulate lunar-like conditions. And the upward flow reactor is a vacuum reactor that allows us to flow in gases if desired to achieve different partial pressures of whichever gas is desired. And so the system works by basically having a quartz window coupled to a beam down mirror that we we use our solar simulator to target the system. And so the beam down mirror shifts the direction from horizontal to vertical. And we have a highly concentrated radiation, and we have a sample holder, an IR temperature sensor that allows us to basically see how quickly this concentrated solar radiation will increase this temperature. And then we have our sealing system, and I think we can get some pretty interesting data based on lunar regolith, and we can capture the gases coming off and determine their composition with mass spectrometry and gas chromatography shown here. And so I believe my time is about up, but that actually works out perfectly because I'll be concluding. And so the first steps towards understanding H2O transport have been presented, and the plans for ISRU research as a part of REVEALS have been previewed. Thank you for your attention. And so here's a quick acknowledgement. This work has been funded by REVEALS, and part of the solar work has been conducted by a team member, or conducted with a team member, Ashley, and my advisors, Dr. Peter Lutznizer. And I'd like to thank all the REVEALS PIs.
Thanks, Thanks, Garrett. So we had at least one question online.
Yeah. Michael wants to know, what is your prediction for water behavior? Will it be more or less efficient at passing through your experiment?
So there's a lot of interesting things with water vapor. One, it will slip more according to that kinetic diameter, but it also could potentially stick and could potentially undergo phase change if I'm not at high enough temperature. So we'll just have to kind of wait and see, and potentially I think I could do a little bit more review and see if I can try to predict any of these phenomena with water vapor. But I basically anticipate water vapor to be a lot more complex than argon and nitrogen. And the way I approached my work was I want to build complexity instead of starting with the most complex and trying to figure it out from there. So.
Okay, Josh has a question on that.
Okay, we have one more question from our online audience. Let's see. So Josh has a follow-up on the 6 kilowatts of solar power. It looked like from the plot that was 6 kilowatts per square meter. If so, that's just 6 times the power on Earth at noon on a sunny day. So I was surprised to see it melting whatever that was in the video. Did I read the plot right for power per unit area?
Oh, I got this plot from my lab mate, and it looks like so it's not the power density that you need to worry about. It's basically the total power, and so this might actually be kilowatts. I would have to double check. Unfortunately, this plot came without that axis label, and I added that in thinking it was watts per meter squared, but it is in fact much higher than 6 times concentration. So that's probably just a slight mistake. And yeah, because of course we can do this.
Garrett, can you comment on the depth that this solar concentration would be effective to? Because the thermal conductivity of regolith in vacuum is so low that what other people have found in these types of experiments is that you just melt a very thin skin on the surface and that you don't actually get useful heating at depth for things like volatile extraction.
Yeah, and that's a reason too why it's not just transport that we would have to worry about. It would be also heat transport. And so I didn't address that specifically in this presentation, but heat transport into regolith, you're right, would be limited because essentially radiation is the only mode that would allow that heat transfer. And that's because you don't have an, at least like regolith without any gas in it, you don't have any gas to conduct heat through that. And so conduction is very limited. And what I think what people have seen, and that you don't get a lot of heat penetration, is an interesting challenge. And I've seen a couple. Now, I'm not working on this specifically, but people have proposed using things like rods, conduction rods, or essentially fins to increase the heat transfer and heat penetration into that regolith. However, that's an interesting challenge. And I didn't mention it here, but I think I'll be looking at something like that to basically see if there's any way we can increase that heat transfer. And like one other idea I had was potentially if we can core this and isolate this system, actually inject some sort of gas into the regolith to facilitate heat transfer better into it. But of course, you would want to have that. You would want to potentially have like a cored sample that you could capture all those evolved gases. So there's a lot of there's a big heat transfer challenge with lunar regolith.
And I have a sort of related type of question. So you're studying these two phases where you have large Knudsen number or low Knudsen numbers, but if we have like solid water ice in the regolith, and then we sort of heat the regolith to sublimate this water ice, do you how significant do you think that the large Knudsen number regime is going to be? Is it possible that we're just like going to skip straight away to pressures that will be low Knudsen numbers, and then the slipping might not be as important?
Well, if we go back to this, basically, so the regolith is actually pretty tightly packed. And so to get completely out of the slip regime, you'd have to get to very, very high pressures. And so that's why I kind of limited it to this side. I don't know if you guys can still see my screen. Yeah, okay. Okay, good. Where this is actually 300,000 pascals. And so that's a very, very, very high pressure. And I think that pressure is probably pretty unlikely to stay in. So I think you'd be kind of more in this kind of slip and transition regime.
Okay, thanks.
So another question about the porosity and the nature of the interconnected pore space in the regolith. The lunar regolith compacts quite a bit in the soil profile, but also it's going to be quite a bit different than JSC because it will be much more angular, much more a result of impact and gardening. Mm-hmm. And so how does that affect your estimation of the distance between your particle walls?
So that's a very good question. I think that could be something that I'm going to look into the future, because essentially I mentioned, and maybe it's this slide, but advances need to be made in not only the fluid characterization, but the characterization of these porous media. Porous media are not easy to understand. We can't just say that the pore diameter is just like half or whatever the particle size. Like there's a lot of different factors that play very complex roles. And so that's ultimately why I chose an empirical relationship, because all these relationships are going to have to be empirical. And so potentially developing a way to determine pore diameter and characterize that the lunar soil is needed. And so hopefully like this correlation right here could be replaced with one that's more appropriate for lunar soil. However, like I said, this one I believe is pretty accurate in terms of JSC1A.
Remind me what you're working with in terms of soil porosity.
I'm just, the way I measured it was I measured the total volume of my bed, and I knew the mass, and so you can find the relative density. And so when I pack it, unless I was to vibrate it, I can't get to higher porosities or lower porosities lower than 0.36, because when you just pour particles into a sample container and then maybe hand pack it, you're going to be limited. And this is called random packing, essentially. And typically, when you randomly pack something, you can get porosities ranging from 0.36 up to 0.42. And so ultimately, the porosity isn't is important in and of itself, but it's also important in how it affects all those other parameters. And so so the porosity, of course, like I said, is used to calculate and characterize like my entire packed bed. So
One thing to keep in mind is the top about 10 centimeters of the lunar soil is going to be about a factor of 2 more porous than what you're talking about, because of the micrometeorite gardening and the regolith fairy castle structure.
yeah.
Or in the immortal first words on the moon, it's soft stuff. I can kick it around with my feet.
Yeah.
And we agree. I'm from the REVEALS team, and we understand your point, Dan. The only thing is Garrett was really advanced in his research, and he's about to graduate with his degree with PhD. And we started all that work with JSC 1A.
Yeah,
and
understood.
we, once he finishes and he wants to go postdoc or whatever, we can switch to the stimulant that are more accurate. But right
Well,
now, that's what we
The
have.
fundamental
It's just-
problem is going to be that it's for the topmost loose regolith layer on the moon. It's almost impossible to simulate that
Yeah.
because of lower gravity, the
And
micrometeorite fluffing, the agglutinitic fairy castle structure. All of these things instantly collapse when you touch them.
Yeah.
But that's really the most accessible way of transporting volatile molecules along the surface. And it's this big fairy castle sponge, which, is going to be hard to model relative to doing spherical cows.
Well, that's why we're gonna get Garrett a postdoc position.
Okay. Well,
But, I mean,
Go ahead.
technically, technically, if we go in for ISRU with the machines and everything, aren't they going to destroy the first fluffy layer anyway?
oh, sure. But,
Yeah.
remember that this is a moon-wide transport
Yeah.
process.
Yeah.
So until we actually start to flatten out a considerable portion of the moon, this is what's going to happen.
And Garrett, just for me to remind me, you're doing your experiments at room temperature?
Yes, at least initially. I'm setting up right now for a higher temperature study.
Thanks. And so our time is up now?
I think our time, is there any more online?
No, doesn't look like it.
Okay.
And also, just a quick plug, I'll actually be visiting Florida and Esther just to see a lot of a lot of your guys' facilities in a couple weeks. So talk to her more about that, and maybe we could meet and discuss about these things more if you guys would like.
Yeah, I
Yes.
just want to point that out too. Yeah, Garrett is going to be visiting in 2 weeks. He would like to join you, Dan and Kevin, to go with the Exolith lab, learn about the microbiome, the mineralogy, and then he's also going to go visit Swamp Works, and so we have a after talk to discuss how we can coordinate all of that, because he's very interested in this work and he's probably going to move forward in this direction. In 2 weeks, he'll be here, October 7th to the 11th. And I'll be
Okay.
hosting him.
I'm gonna be in Luxembourg.
Okay. So
Are you going to be in Hawaii? Okay. So Kevin will be around, and he knows more about it than I do.
well, we can, we can stay in touch. He has set up that for some meetings, but he can, he's not that far away, and I have room and board in my house. So
Okay.
he's all right.
All right. Very good.
Okay, we'll be happy to meet you,
Oh,
Garrett.
And then Wesley will be interested in talking to you too, Garrett. Yeah, you can say something.
I'm looking at plume surface interactions. So the calculations you're doing as far as porosity and permeability and things like that, I'd be interested to talk to you about that and show you some results I'm getting. So it's a little more complicated, like not looking at it just gas flowing through the regolith, but pluming it and then looking at how it reacts in microgravity. But yeah, I'd be interested to get your thoughts.
Yeah, that sounds really cool.
Well, let's stay in touch with Dan Braid, okay? Because he might be leaving, but just for a few days while you're here. But stay in touch with him, okay?
Okay.
All right. Thank you again.
Thanks, Garrett.